touching the earth, so there's no friction between me and the earth, but there does need to be, the two objects, there needs to be a desire for one of them to slide. And the reason why it's desired is it doesn't necessarily have to slide in order for there to be friction. So right now, there's friction between my feet and the ground. If the ground were frictionless, my feet would go flying out that way. So I'm not moving, but my feet have a desire to slide that way. So there's friction there. Normal force, the requirement is two touching objects. There's a normal force between you and the chair, between me and the ground. Or if you really want to get nitpicky, actually between me and my shoe, or me and my sock and my shoe, the shoe and the ground. I refuse to admit that the shoes are part of me. All right. Cruising along. When dealing with forces, there are a couple of rules. Forces come in pairs. Oh, I left other off. I'm going to jump back and then come back to this. The requirement for other is there exists a force. Now, we've talked before about how we hate writing, and so I'm going to do a shorthand notation for there exists. And that's the backwards capital E. That just means there exists. There exists a force with an unknown source or an irrelevant source. And it's quite possible I've got some of the vowels wrong and irrelevant, but an example of the problem that we just did, I said there was a 10 Newton force pushing on this box and another 10 Newton force pushing back. I don't know if I told you what caused those forces, I just said that they existed. That would be an example of other. So textbook problems typically have an other in there. So forces come in pairs. So when we do our force diagram, we're going to be doing the pairs unless there's another. The other forces are ones where we'd only draw one part of that pair. The other force exists, we just either don't care or don't know what it's acting on. But forces come in pairs. And I'm going to write the word always there. There is one very obscure exception to this that is well beyond the scope of this course, and matter of fact, beyond the scope of any of the stuff that I did in physics also. But there's a very rare exception. But I'm going to throw in the word always. Try not to use always lightly, but for anything that we're doing in here, and matter of fact, unless you are dealing with, I guess, astrophysics, that's the place. If you get into astrophysics for your PhD, you might run into the exception. Each force of that pair is the same type. What I mean by same type, there'll be two weights or two gravitational forces, two normal forces, two tensions, two frictions. Is the same type, acts on different objects, and acts on different objects in opposite direction. And have the same magnitude. I was gonna tack this on and then I realized I should throw that in first. That's why I crossed that out. It was easier than erasing. Now, of course, there's a shorthand way of writing it. I'm just gonna write the shorthand up here. It doesn't necessarily make sense at this point. It will come back later. But the shorthand of this, the force acting on A from B is equal to the negative of the force acting on B from A. That's the shorthand version of this. Give a dramatic pause for people to catch up on the writing, and if there are any questions. Something as simple as, what does that word?
Why do the D and the A switch?
When you do the notation like that, when they represent objects, the first letter is the object the force is acting on. The second letter is what's causing that force. So this would be the receiver and the source. When we do a force diagram, we will be drawing forces on the receivers.
When you say they come in pairs, is it like the same when you said like the 10 newtons going both ways? Or are those the pairs?
Those are two separate forces, so each of them would be part of a different pair. An example of a pair is I weigh about 220 pounds. The Earth is pulling on me with 220 pounds of force. I am pulling on the Earth. I'm pulling up on the Earth with 220 pounds of force. So there's a force acting on me, there's from the Earth, and there's a force acting on the Earth from me.
Okay.
That's what I mean by the pair. And we are about to do just a slew of examples where, oh, it'll be a non-stop thrill ride. I'd like to say true story, but I guess we'll find out. All right, since they come in pairs, and we will be drawing pairs of a lot. So how we draw them with respect to the pair. So when I draw them, for example, friction, when I draw one of my friction forces, the other one is going to be parallel to it, or actually anti-parallel to it. You'll be drawing them on the surface, and they're going to be sort of overlapping like that. There'd be two objects here. This would be acting on one object. This would be acting on the other object. Tension, when I draw a tension, the pair of forces will be pointing towards each other. Other is problem dependent. It points, since you only draw one of those pairs, we're not going to worry about other right now. Weight or gravitational force, when I draw those two arrows are always going to be pointing towards each other. Or actually, in case of weight or gravitational forces, they're pointing towards each other. And normal force, those pair of forces will point away from each other. So I'm not falling through the ground because the ground or the carpet is pushing up on me with a normal force of, if I'm standing still, about 220 pounds. And I'm pushing down on the carpet. So the force on me is up, the force on the ground is down. So they're pointing away from each other. And then I did not give myself enough room. Questions before I do the sort of the last tableau or table column? That's it. The last column? Yes, Chase?
Tension be the other way. The force factors you on the opposite way.
Tension is a pulling force, so if I have two objects, let's say that there's, I feel like he said died since I got here an hour ago. If I have a box here and a rope attached to it and I'm pulling on the rope.
Yeah.
The force on the box is to the right.
Yeah.
The force on the rope here at the point of connection is that way. So the rope is pulling on the box to the left, the box is pulling on the rope to the right.
Okay, I'm with you.
And then there's another force over here.
Yeah, I'm with you.
But this is the pair that I'm talking about.
So you're talking about the tension in the rope, really?
Talking about the tension that the rope exerts on whatever it's pulling. And likewise, the tension that whatever's being pulled is exerting back on the rope. I feel that there's a distinction in the slight difference of language that we use. All right, so I'll stick it over here. So how you draw them with respect to the objects, and that is objects plural because you need two objects to create a force. Friction, these will be parallel, again, shorthand notation, parallel to the surfaces of contact. Normal force, those forces will be drawn perpendicular to the surfaces of contact. So normal force is perpendicular to the friction. Weight, or gravitational force in general, it is toward the center of mass of the other object. What are the chances that the people in the back can see this?
No.
I got a no back there? Okay. The direction of I'm gonna, what if I stick it down here with a better marker? This is toward the center of mass of other object. So the force of gravity acting on me is on me pointing downwards towards the center of mass of the Earth, which we assume is the center of the Earth. And the gravitational force acting on the Earth from me is pointing up towards my center of mass, which is somewhere around here. Let's see if I can darken that up some. And this is perpendicular. Surfaces of contact.
What does it say for friction?
For friction, parallel to surfaces of contact. In terms of normal force, I have two normal forces acting on me right now. I have a normal force acting from the carpet and a normal force from the wall. The force on me from the carpet is upwards. The surfaces of contact are horizontal, so it's perpendicular to that, so it's up, acting on me, down, acting on the ground. With the wall, the normal force the wall exerts on me is that way. The force that I exert on the wall is that way. It's perpendicular to that surfaces of contact. Other questions before we still have tension to do and then get into the force diagrams? All right, tension. Tension is the long, usually 1L, along the line of the taut rope, chain, whatever's doing the pulling. start the force diagram. I'll let you just know right now, we're eventually working up, we'll start with simple examples, we'll eventually work up to a test level problem. The next to the last question on the first test will be a force diagram problem. All right, so we'll start out with box falling. First, I'm gonna draw the problem. I have ground. If we see little hash marks like this means that we're assuming that it's, for the sake of the problem, it's not moving. The ground is at rest. And I have a box falling. Not that we're dealing with air resistance here, but that little trail's there to indicate of some sort of motion. So this is box falling. When I do my force diagrams, the first thing I do is I draw the two objects separate. Now they are separate in the drawing already, but just out of habit, I'm gonna draw my box here, and I'm gonna draw my ground here. This is where I'm gonna do my work. That's just posing the picture of what's happening, although it looks like the box has a skunk in it, but let's go with this. And now I go down my checklist. So first off, can we eliminate anything? Are there any of these forces that definitely are not in this problem? Why is there no friction?
Because it's,
There's nothing touching.
yeah.
Exactly. All right, so friction, gone. Anything else?
Tension.
Why no tension?
There's no rope or chain.
Gone. Anything else? Why no normal force?
There's nothing touching.
Gone. Now we're left with just other and weight. Other. Is there any force that I mentioned in the problem without any source? Is there anything like hand of God? Is there anything additional mentioned? So no other. The only force we have left is weight. Yes?
Is it possible to have multiple at one time?
Multiple of each of those? Yes, there
Can you
is.
have like friction and, weight?
Oh, absolutely.
Okay.
Yeah, I'm just starting at, the simplest example is box falling with no air resistance.
Gotcha.
Don't worry, we'll get there. And we'll have multiple weights and multiple, okay. So weight is acting towards the center of the other object. There's a gravitational pull between the box and the ground. So I'm gonna draw an arrow down right there, weight, and label it with a W. And then I'm gonna draw one acting up on the ground. It's an attractive force, just paralleling it over here. The gravitational forces, the two arrows point towards each other, which they do. And it is pointing towards the center of mass of the other object. If I take any object and I let go of it, and it falls, it's gonna fall towards the center of the mass of the other object. Down is defined by the direction of that pull. Done. There's your first force diagram right there. Now, if you're looking in textbooks or sources online or other things, you might hear something known as the free body diagram. I refer to this as a force diagram. Free body diagrams are very convenient. Free body diagram, I would draw a dot here, label it box. I draw a dot here, label it ground, and then I draw my weight acting down there, my weight acting up there. So the free body diagram is the same thing, except they use a dot to represent the object as opposed to something bigger. My undergraduate degree is mechanical engineering. Sometimes it does matter, and eventually for us too, but sometimes it does matter where the force is applied, so that's why I tend to draw the objects, because that's gonna be more meaningful later on than just the single dot. So, just in case you run across free body diagrams, it's the same thing other than the size of the object drawn. Questions before we do box on ground? All right. I'll get that. Box, ground. First, I'm gonna draw a picture of what's going on here. In case you weren't quite sure what a drawing of a box on the ground would look like, but let's establish ground. First thing I'm gonna do is gonna draw my two objects so I have some working space here. I'm not claiming that the box is in the air now. What I've done is I've drawn the box, I've drawn the ground. You don't have to draw them in the same orientation, but I recommend it. The box is above the ground in the problem, and so I'm gonna draw the box above the ground. Sometimes you run out of space when it gets more complex, but as best you can. We've got our checklist. Can we eliminate anything?
Tension,
Why?
there's not a rope.
Go for something more stunning than that. There we go. Oop. Oh, we're gonna change the color. There we go. Tension gone.
Friction, there's no motion that's happening, just on the ground.
No desired motion. Yeah. Friction's gone. There is contact, so we have set aside that piece of it, but it's not gonna slide one way or the other if we're frictionless. Friction's gone.
Other.
Yep, I mentioned nothing in the problem to make you think other would be involved.
Wait,
You saying there's no weight?
I said wait.
You saying weight is there or not there?
No. Yeah, not there.
Why would there not be weight? Do we have two masses in the problem?
Yeah.
All right, is one of the masses small relative to the other one?
Yeah.
So weight's involved. Yeah, assume that the ground here is part of a larger planet. It's not just some tiny little piece of land. All right, so weight is involved, and there's two objects touching, so there's normal force involved. All right, so let's deal with weight first. Which way is weight acting on the